Okay, so let's put things a little bit in perspective, okay? So I think everybody has now seen what's on the exam and what's not. RLS, recursive least squares, is on the final exam. It's not on the midterm. So starting with RLS, we're doing material for the final exam. So we've been solving overdetermined equations. When you do that, there is no x such that c times x is exactly equal to the measurement. It just doesn't exist. Okay. So really, even though we weren't writing it down explicitly, there was something that was causing these equations to not be correct. And what we were doing, remember, is we took y minus c times x, that norm, and we tried to make that small. So what were we really doing? We were minimizing what we have to add to the equations, what we have to pull out of the air to make the equations consistent. Okay? Minimizing y minus cix is the same thing as minimizing ei. It's minimizing what we have to add to make the equations correct, the uncertainty. Okay, so with Niels on Thursday, while I was out in California, you guys learned how to approach the problem in two different ways. One, if you have a whole bunch of measurements, you can just wait and process them all at once. You get another measurement, you have a bigger set of equations, you reprocess that all again, you get one more measurement, you reprocess that all again. And so what you would be solving is your best guess of what x is minimizing the weighted norm of the uncertainty in the equations. And then a better way to do it would be, look, I've already solved the problem at time k. I get a new measurement. I can predict what I think this measurement would be based upon my last x, right? Okay, so this would be my guess at the measurement given the previous one, because x is constant in RLS. It's not moving. This difference here is something I've learned, okay? The measurement gave me new information because it was not exactly the same as what I predicted it would be, so I've got more information about x, and I take that new information with a gain, and I get my new best x estimate. So that's recursive least squares. Taking your current best guess at the state and correcting it when the new information comes in. Now, some of the stuff that's bugging you a little bit right now is, where does this come from? Okay, how do I choose it? Do I just go like this? Do I ask my neighbor? So what we're working towards is coming up with, A, how do you choose the weighting terms in weighted least squares? And then how do you handle problems where this thing I'm trying to estimate is not a constant? What if x is moving? What if it has dynamics? Can I do something recursive as well in order to form a new estimate of x based upon my past estimate of x and my latest measurement? A recursive formula for coming up with a best estimate of x. Does that seem interesting? Sort of, maybe, partly, tiny bit? Okay, not so much. Okay, got it. One of the things you're going to explore in homework then is just the basic speed of this batch operation, this standard form of recursive least squares, where you are inverting a matrix here that is the size of the state. In your homework example, n is 100. And then you're going to compare that to a modified version, which uses the matrix inversion lemma so that you are inverting a matrix that is the size of the measurements. So in your example, that's 3. Okay? You have 3 sensors. You've got a state vector that has 100 components. You can invert the 100 by 100 matrix on your little microprocessor, or you can invert the 3 by 3 matrix. Which one would you prefer? Okay? It's pretty clear. So that's where the matrix inversion lemma comes in, and it gives you a updated, slightly different formula for calculating the optimal gain. And what that is doing, and let's think about it this way, it's fusing my current estimate of x and my new measurement to get my next estimate of x. It's fusing these 2 pieces of data. So you probably heard the term in a seminar, data fusion, okay? I'm just planting that seed, data fusion. Okay, so your homework compares all of these things. Now there's one question I've heard so far on homework on this initialization step. You have to start somewhere, so you need to solve an overdetermined problem because that's all you know how to do. So you do have to solve one batch problem, but you solve it only once. You wait until you've accumulated a set of measurements that is big enough that you have an overdetermined problem. So when you stack up y from 1 to capital N, and you stack up these matrices, you get 100 linearly independent columns. Now, if y has 3 rows, how many time steps minimum do you need to get the rank to be 100? 3 times 33 is 99. If you have 99 rows, what's the maximum rank? 99. It's not 100, right? X has 100 components in your problem. So you got to go at least 34 time steps to get 100 independent rows, okay? After that, you can then use this recursive form. So you initialize, you'll have to go to little n equals 34 in your homework problem. You can check it. But it could be that you take 34 measurements and it's still rank deficient, and you need 35, 36. You need to check until you get a full rank matrix. That's all that's going on there. Okay, so I should get you going on the recursive least squares. Now another way to initialize, which is what we're not doing in this homework problem, but it would be a reasonable thing to do. What if I wanted to initialize at time 1? So this is 3 in your homework problem. X is 100. Okay? What's the problem with 3 equations and 100 unknowns? Nothing. No, sounds good to us. Well, you don't have enough information to determine a unique solution, right? There's an infinite number of solutions. So which one should I take? The right one? There is no right one, okay? So you might like to have a way of choosing amongst those infinite number of solutions. So that's what underdetermined equations are all about. So overdetermined was AX equals B, and you have more equations than you have unknowns. Underdetermined, you have fewer equations than you do unknowns. And so I'm going to give you the magic formula for solving for X that has the smallest norm amongst all solutions. So this will be like when I gave you the magic formula for the overdetermined based upon my undergraduate regression handout, and then we derived it using the normal equations. I will have you derive this in homework, why this result is true. So with the idea with underdetermined equations is there exists an infinity of solutions, and we're just going to choose the solution which has the smallest norm. So what is the x of smallest norm that makes this equation hold true? And so once again, we'll do a weighted least squares. We will learn a little bit later when we do best linear unbiased estimators and minimum variance estimators where this S comes from. Right now, it's just a design parameter that we can play with, okay? But we will learn when we do these other estimators the source of the weighting term, a very natural source. Okay, so we take our weighted least squares, so the S norm of X is inner product X transpose SX, S positive definite. We're going to find X of smallest norm that satisfies the equation. And then here's the theorem. So I posted all of this on in Canvas. X hat, which is argmin over all x's that satisfy the equation, okay? And then here's the norm. It's X transpose XS, SX to the square root is given by this formula here. Okay, it looks just as mysterious as the overdetermined one did initially, but you will derive it in homework and you'll find the normal equations that yield that answer. And so we will use this a little bit later, if not Thursday, by Tuesday of next week probably. Okay, questions? Yes? A little bit louder? I guess I still didn't get it.
Your mic's rubbing.
Oh, my mic's rubbing again. Let's see. I was expecting an answer on the question, and my Kalman filter didn't process the other part. Let's see. Is that better? Still rubbing? Is it? To the beard? Will that be better? Hey. Okay. You just wanted to see me dance. I got it. Okay, any questions about underdetermined equations? So it's just a way of choosing amongst all of the solutions. Just like before, there was no solution, and what we were really doing is, what is the solution for X that I have to add the smallest thing here to make sense of the equations, right? So this is like a measurement uncertainty. How much noise do I have to add to explain the data? That was the overdetermined case. Okay, so that's our start on estimation. So now I want to get us on the road to the famous Kalman filter that you've heard so much about. And we're going to take little baby steps to get there, but in some sense, recursive least squares was your first baby step. So here's the idea. So imagine we just have this vehicle, our mobile robot. The acceleration is 0. Okay, so it's moving at constant velocity, except there's wind gust and drag and things like that. Okay, so we're not applying any torque at the wheels. So for far as we're concerned, the acceleration is 0. And our ability to measure all the stuff that's affecting the cart here is going to be not so easy to do. We're not going to have a mathematical model of the wind that's blowing that day. Okay, so we're going to take a probabilistic description of that. It'll have a certain mean and a certain spread about the mean. That will be the variance. Okay, so that's what's pictured here. Is initially we don't know exactly what the position of the cart was, We now know its velocity is constant, subject to deviations from the wind. So now if I take and propagate this forward in time, what's going to happen to my uncertainty about x? Well, what happens when you have to propagate forward your bank account? That one is easy. You know it's always going to 0, right? So that one you have a lot of high certainty on, okay? But no, do something else, okay? Propagate forward the weather given your observation of what you just made an hour from now. Now, an hour and 2 hours, your uncertainty grows. Okay, so 1 minute later, this might be our estimate of x. It's spread. Why? We had initial uncertainty in the cart, and it's being perturbed by other uncertainty here, so that's causing the uncertainty to grow. But now we have these things called sensors, and we make a measurement. Okay, so if I just propagated forward my uncertainty, you know, here's my mean value, and I've got a certain standard deviation, and we will define these terms precisely in a second, but we have a spread about that mean. Unfortunately, my sensor is not perfect either. Imagine it's a LiDAR. It's sending a pulse of light, it's bouncing off, it's coming back. Okay, the speed of light, that's pretty constant, but my ability to measure the time duration is what's not perfect, okay? We're talking nanoseconds here, and my ability to measure that perfectly is lacking, and so I have a spread about my sensor measurement. Now, how do I take the information that I have about where I think the cart is? Now I have my information in the measurement. How do I fuse these two pieces together to get the best estimate of the cart? That's the problem we will be solving. So x at t has some probability distribution. Our measurement is not perfect, so it has some probability distribution. And we want to fuse it to get the very best estimate that minimizes the error in our estimate. So how to fuse, and the word fuse just means combine, okay? How to combine the two pieces of information to get a single best estimate of the state. Okay, so now when you guys did RLS with nils, x is constant. So if I look at a discrete time model for how my state is evolving, you guys had x as constant. That means this was the identity matrix. You have, it gets initialized to a value you don't know, but then it just stays there, and then you just take measurements of it. Also, when we did RLS on Thursday with nils, there was no perturbing noise term in the dynamics either. We had a measurement. It was assumed to be deterministic. We didn't have a description of how the perturbations in the sensing arrived. All we knew is, in general, we never had an x such that y minus cx equals 0, and we just tried to find the best estimate of x to make the measurements consistent. And what we were really doing is minimizing how much we had to fudge the equations in order to make them consistent. That's what we were doing. So now we're going to take a little bit broader view. Not yet, it's going to be a couple of weeks down the road, but we're going to add x is evolving in time. There are perturbations like the wind gust in them, and we have sensors that are related to the states, and then there's uncertainty in those measurements as well. And based upon that, this is the cool thing that we will do. We will find the best estimate of x at, let's do this one, the best estimate of x at time k given all the measurements up to time k. Oops. It's okay. It's happened to me too. The best estimate of x at time k, so this will be, we'll call this a conditional expectation. So today we'll study expectations. We won't be doing conditional expectations, but this will be the best guess of x at time k given all the past measurements. And we will find a recursive formula for that that looks remarkably similar to recursive least squares. Okay? Except now, the s, the weighting term, it's going to come from the spread we have in the initial condition of x. And did I define the other terms? Oh, no. And then it will come from our probabilistic description of how the noise is affecting the dynamics and how the noise is affecting the measurements. So the weighted least squares problem will come from physical data. Okay? So the weights will come from the relative certainty of the measurements versus the state. If the state model is super accurate and the measurements have lots of noise, then your corrections will be very slow in the measurements because you don't trust them very much. And if there's a lot of uncertainty here and the measurements are very accurate, you'll do a very fast updates because you trust your sensors, okay? Now, how do you choose those? Well, you need to build the model of your dynamics, how it's perturbed, your sensors, and it's perturbed. That's not easy. We don't go through the modeling stuff, unfortunately, in Rob 501. You'll see more of that in the mobile robotics course. Name EECS 568, and I forget the robotics number it just got recently. Like 510 or something, I forget, okay? So the Kalman filter really looks like recursive least squares. It is recursive least squares when you add in all of the dynamics. Cool? Sort of? Okay. Anything else? So now we got to start filling this stuff in. No more questions? You want to delay the probability review? Get going? How many of you have had a probability course as an undergrad? Just curious. About 30%, yeah. How many of you had one and then didn't want to raise your hand because I would assume you know something? Okay. Okay, so maybe it's 40% of you who've seen probability before. So that's the thing. So we're going to do 2 different reviews in the course. This is the first one. So if you've had a course, this is going to be super elementary, and if you want to leave, I don't care. My ego is not on the line here, okay? So I want to define, a probability density. Okay, so F takes R to R is a probability density for a continuous real valued random variable, which we'll denote by capital X, if Three things hold. Okay, so random variable. Easiest example is a dice, or even easier, a coin, okay? Those are discrete because it only has heads and tails, or 1, 2, 3, 4, 5, 6. Continuous random variable means it's not taking discrete values. It can take any value in an interval. So for example, the speed of the wind. Okay, probably it can't go faster than the speed of sound, okay, and in different directions, but we would model it as a real continuous random variable. So the first thing should be, if it's a density, for every x in x, f of x is non-negative. If we integrate over the entire domain, we get 1, so it's normalized. And then there's one more part I need to add, because for today we are skipping the more fundamental review that we'll do a little bit later. If I have two real numbers, x1 less than x2, then the probability that x takes values between x1 and x2 is probability x1 less than x less than x2 is equal to integral x1 x2 f of x dx. Okay, so I have to add this because really the more fundamental quantity when you talk about random variables is the notion of a probability. And a density is a way of easily computing or describing how that probability is determined, okay? So, simple example. Whoops, come on. Uniform random variable. Has density on AB, A strictly less than B, given by, oh, I hate it when it does that. I still haven't figured out how to stop it. Bingo. Given by f of x equals, well, it's 0 if x is less than a. It's 1 over b minus a when x is between a and b. And it's 0 when x is strictly greater than b. Okay, so what if you have a uniform distribution, the probability that your random variable takes values between here and here is just the area underneath the density. Okay, that's all that the integral is. The more important one for us is going to be the Gaussian or normal distribution.
So it has a beautiful formula. 1 over the square root, 2 pi, quantity sigma squared, E, then there's a ratio. Come on. X minus mu squared, 2 sigma squared. And it's typically written as normal, excuse me, not X, mu and sigma squared. Be nice if it's sort of a bell curve, right? Yours look nicer. You didn't. You're smart, Sabrina. You didn't even draw one. Okay. We're going to take a chance. Okay. I got it. And so if this is x1 and this is x2, this is the probability that x is greater than x1, less than or equal to x2. Okay, so the density gives you something that pretty soon we're going to call a mean value, and then a spread about that, which we'll call a variance. Everything here seem okay so far? Okay, so it's a description of how if I just keep drawing values, this is how the numbers would look. They would all, a bunch of them would cluster up about the mean, and then there'd be fewer and fewer that were very, very, very far away. Okay, so let's define this mean value. Okay. Mu, by definition, we'll call it the expected value of x. Okay? Is simply you integrate x, f of x, dx. Okay? Everybody know what AKA means? AKA, also known as, okay? The average value or the expected value. Okay, so if you want the average value of your random variable, you integrate x against the density. In general, okay, let G takes R to R be a function. The expected value of G applied to your random variable, all it means is you integrate G of x against the density. This is called the expectation operator. So when g of x is equal to x, then g of x is equal to little x. It's just the mean value, okay? You can take g of x as x squared, and you do x squared, it's called the second moment. And then you take the third power, it's the third moment. You get these things called moments, okay? So you can do expectations of all sorts of different things. So we'll make one more choice of g in just a few seconds. Let's go back to our examples. Okay, so if we do 1, f of x is distributed with the uniform. So I'll just do with the picture. 1 over b minus a. Okay, so we have a uniform density. Can anybody do this integral for me in their head here? Yes, all of us can, Professor Grizzle. Okay, so that's the mean value of a uniform random variable, b plus a over 2. Okay. Sigma squared. Okay. Now the mean value of this you need to integrate x, this minus infinity to infinity, and when you do it, you get this parameter mu, okay? So you might want to do it at home just once. I don't think I've done it for 32 or 4 years, somewhere along in there, okay? I did it once as a young boy, okay? So this is equal to the expected value of x. So one thing I just want to point out about these normal or Gaussian random variables is the quantities that we care about, we just be able to read directly from the density. We will not be doing a bunch of integrals, okay? So on your final exam, you will not be doing this for some crazy function and some crazy density. That will not be happening, okay? It's just not what we do in Rob 501. Okay, so that's the mean. The key thing we want is the spread, and that's called the variance. Oh, come on, be nice to me. Variance. Of a random variable. So this is really the spread about the mean value. So variance of x is by definition equal to expected value x minus the mean squared. Okay, so in principle, this is the integral you're doing. You first calculate the mean, you take x minus the mean, you square it, and you integrate it against the density. So if the variance is small, it's concentrated about the mean. If the variance is huge, it's all spread out. And even though you're reading the sensor value, and you know on average it gives you the right thing, It may be lying to you 99% of the time with these huge errors, okay? So that's the thing you want to know. So this is what you want to be small, the spread about the mean. You want the variance to be low. Okay, so this expectation is just an integral, right? So this is an integral of something squared. What does that sound like to Rob 501 students? It's a 2 norm squared, okay? This is a 2 norm squared. This is just a weight, okay? This is a weighted least squares. This is just a weight, okay? It probably has really high values about the mean and very low weights far away in the tails, okay? This is a weighting term. That's what the density is. That's the Q when you're doing X transpose QX, okay? It's just the weight. The density is just the weight. It's the spread. So it's a 2 norm squared. Squared for random variables. Okay, so once we understand that maybe our estimate, we're trying to find an estimate for a quantity that minimizes the variance, okay? So our estimated value will be the expected value, the mean. And we want to choose that value that minimizes the uncertainty about that, okay? So if that's really a least squares problem, you can solve it using the normal equations, okay? And that's what we will do for the minimum variance estimator. It'll just pop out. Once we define the correct set of vectors and we define the correct inner product, it will be a set of normal equations. Okay, so what's the variance calculations, just as on our examples? So for the uniform random variable on AB, variance of X is equal to expected value X minus the mean squared, and the mean was B plus A over 2. So this equals the integral from A to B, X minus B plus A over 2 times the density, 1 over, squared, dx. Okay. Check this at home. And you'll get 1/12 B minus A squared. Okay, so once again, in general, for a given random variable which has a given density, this is the variance, X minus the mean. You integrate against the density, and then you have to do an integral, okay? For the normal density, m mu sigma squared. Okay. Expected value of X minus mu squared equals integral minus infinity to infinity X minus mu squared times that normal density that I'm not going to copy in, but you just get sigma squared, okay? So the normal density is written down, so it's parameterized by its mean and its variance. And then you get these beautiful pictures. And you'll find that 67% of the time you're within one standard deviation of the mean and stuff like that with these, okay? So there's little rough parts. Okay. It's a good time for questions. What have we just reviewed? Something called a random variable. So this is something where we don't have certainty of the value it is taking on. It's like rolling a dice, except it's a continuous die now. It's described by a density, and the key thing about a density, because this is an infinitesimal probability, it can't be negative. The probability of a 1 on a dice is -2, I don't think so, okay? Maybe low if your dice is loaded, but it's still non-zero. And you add up all the probability, you get 1, so it's normalized. And in general, to calculate probabilities, you're doing integrals. And then we define the mean value. We define in general the expectation of any function of x as just g of x, and a really special function is x minus mu squared, and we get the variance, which is the spread about the mean. Okay, and these things that are called normal random variables or Gaussian random variables, they're parameterized by their mean and their variance, so we don't do any calculations at all. Okay, that's what we have so far. So that's kind of undergraduate, sophomore level, junior level probability, okay, depending upon what program you were in. If you're from China, you did this in high school, I know, okay? And all of the American students are embarrassed, okay, that we didn't get to do that in high school, okay? So I'm boring you guys to death. I'm very sorry for that. Now, how many equations do we find that are interesting that have only one variable in them? And the answer is in engineering, not enough, okay? So we're always having to deal with vectors. So we need to now talk about random vectors. How many of you have seen random vectors before? 2, 3, 4, 5, 6, 7. Okay, so I just want to review random vectors. To get the concepts down. So now our x is going to look like this. x1, x2, xn. Okay? Where xi is a random variable. Where we are going with this, eventually this axis, some of these components will be things we're trying to estimate, and some of these components will be measurements that we're actually making. And based upon the measurements, we want to update our knowledge about x. And this is going to lead us to that sure complement that I talked about, where you have uncertainty in this, you have uncertainty in the measurement, but you make the measurement. In general, you reduce the uncertainty by the sheer complement process, okay? So the problem with random vectors is these guys are all connected in general. If they're not, they're said to be independent, which is a different type of independence than linear independence in vector spaces, okay? So the problem is this density, come on. Now depends on little x1, little x2, and little xn. At each point, this is an infinitesimal probabilities, and the probabilities cannot be negative, so they're non-negative numbers. And then to add up all of the probabilities, you have an iterated integral. Fun! Oh, I can't wait to do these, Professor Grizzle. I love doing 9-deep integrals. I mean, it's just one of my favorite things in the world to do, okay? And that should add up to 1. Okay, so in general, random vectors are a pain. They're really painful. Okay, so the density depends upon x1, x2 through xn. So just specifying this function can be really complicated. And then calculating anything with it, you're not just doing one integral, you're doing 2 integrals, 3 integrals, 4 integrals, etc. And so, you know, like my robot, it has 40 states, and we're making about 15 measurements per millisecond on it, okay? So that means I've got a 55, my little n is 55, okay? Because I've got my states and all my measurements. Those are all my random variables together. No, so you want to do a 55 deep iterated integral? No, okay? So it's really, really important then if you can work with probability descriptions where you can pull out the relevant information in a much more simple way like we did with the normal distribution, okay? So that's what I want to lead you to. Eventually we're going to be doing normal random vectors, and you're going to learn more about those than you ever thought humankind could possibly know, okay? And that's what we'll use to derive the Kalman filter. So for these, though, just so we can get started on estimation, I want to define the mean vector. It's no longer a mean value, it's a mean vector. Okay, so mu, by definition, it looks super innocent. We just write it as the expected value of our vector, okay? And it is just the expected value of the first component and the expected value of the second component, etc. So that's all, in principle, super straightforward. I guess I do that just to give you time to write. Okay. And so this is mu1, this is mu2, dot, 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 mu n. Okay. Okay, let me change. So what integral do I have to write down to calculate the mean of the, say, the third component? You know, so the expected value of x sub I is this iterated integral xi f of x1 xn, I don't know. Okay, so we have to do that for I equals 1, I equals 2, I equals 3. It's the same idea, I just average out the probabilities. I'm adding up all the probabilities weighted by the variable x1 and then x2, et cetera. But I'm doing, for my robot, a 55 deep iterated integral. No fun. Okay, so we don't do them. Okay, so but that's what the mean value is. Okay, so that's kind of easy. It's the mean value of each of the components. And to compute that, you need this density, which looks super complicated. And this is the key thing I need you to understand, the covariance matrix. Okay. So Q is by definition equal to, it's x minus its mean vector times x minus its mean vector transpose expected value. Now that's n by n. This is n by 1. This is 1 by n. Okay? What is the ij element of that matrix? Okay, so if I just do this, it's this expectation, it's the spread of the ith random value, random variable, minus its mean times the jth random variable minus its mean. Okay, so of course that's 1 by 1, the ij element. When I and j are equal, this is the variance of the ith random variable, the component of x. So this matrix has all of the variances on the diagonal, and these are called correlations. We don't need that vocabulary right now, but this is how the ith random variable is correlated with the jth random variable. And our hope is that if this is a state variable and this is a measurement, this correlation better not be 0, okay? We're not getting any information out of the measurement about that state variable, okay? So if they're completely uncorrelated, then that measurement is worthless. Just throw it away. Okay, so this is the spread about the mean vector, but it's a matrix, so it's hard to picture. So I'm going to try to work towards a picture of it in a second. Questions? A good time to pause for questions? What's your fun factor right now? Let's make it a probability. 0.7? No, it's really a normal distribution, and my fun factor is way out there on the tail. It's not having any fun at all. Got it. Okay. Did I get it? Yeah, fact. This matrix Q is symmetric, and it's positive semi-definite. So it's always at least positive semi-definite. Okay. in our work, we will always assume Q is positive definite. And why we need that is unclear for the moment, but it will arise in a little bit. Okay? So this matrix, when its diagonal terms are small, then we know a lot about how X is doing by just knowing its mean. And when the diagonal terms are huge, then it's just this huge spread and we don't have very much information when we make a measured value, okay? If it's small, when we make a measurement, there's a really high probability that it's around the mean value of the sensors for that value, okay? So this is the spread. And then the correlation, the off-diagonal terms, that we will build upon because some of these will be states, some of these will be measurements, and this is telling us how strongly the measurement is related to the state value that we care about. Okay, so let me see if I can put in some pictures because my drawing doesn't work, for you guys anyway. Works for me. Let's try this one. Oh yeah. What happened? Where'd it go? Oh, there it is. Okay, and let me put in one more. Bingo. This is much prettier. Okay, so these are bad pictures, they're grainy, sorry about that, but this is what would be happening if it's a normal distribution. You just sample it and sample it and sample it, which is equivalent to just rolling the dice, okay? I'm getting a value from my sensor, I get another value from the sensor, I get another value from the sensor, get another value from the sensor. My sensor has two components, and I start plotting them. Where the probability is high, I'm gonna get lots of dots, dark. And where the probability is low, I just get a few values because I'm out in the tails. I don't get those very often, okay? So this is showing, here's the mean, where I've got the most data samples showing up. This is if I integrate out the X component and I get the marginal distribution for density for Y. You did that in homework 2. This is if I integrate out the Y component and I only look at the X component. So this would be, I simply don't plot the Y and I just looked at the X's. I just take and project them here. That will average out all of the Y values, okay? That's the density for the X's. If you look at the picture, this is a two-dimensional normal distribution. So the tails are in two space, okay? It has a mean vector and it has a spread. And they can be very different in the X direction. So this is tighter in this direction and much more uncertainty in this direction. Okay. Now, no, I don't want to do that. I want to do this. So, Q big implies lots of uncertainty. So if Q is small, this would be up like a needle. Okay, so if this was all just looking like this and this thing went up to like 100 because you had to get a really small area to get 1, okay, then you know that it's going to be with a really, really high probability by the mean. So Q big, we talked about this before. Q inverse is then small. Q inverse, once again, is called the information matrix. Okay, so suppose Q looks like this. 10, 0, 0, 0.1. Okay, I'm making it really simple. The off-diagonal terms are 0. There's no correlation between the first component and the second component. Now, suppose this is my expensive IMU. The KVH, just sub-military grade, okay, that can actually measure the rotation of the Earth. Okay, and this is my cheap sensor that I can buy for about $2. It's a MEMS little device, okay? So, this one here is 100 times more accurate. It's actually about 10,000 times less drift in it, okay? So that's what that means, okay? So then Q inverse is 1/10, 0, 0, 10. So we have, in this case, 100 times more fidelity, 100 times more information in X2 than in X1, right? So if X1 and X2 are random variables, and this is the random vector, when Q is diagonal, it's really clear if these are measurements, which one is more valuable and which one I should trust more. Okay. Now, look at this. Suppose Q, for example, equals 2, 1, 1, 2. Which of my sensors do I trust more now? Can I combine the sensors and get one that I really trust? Okay. This is called a symmetric matrix, right? Okay. So I can write this as O transpose. This is 3, 0, 0, 1 times O, where my orthogonal matrix is 1 over square root of 2, 1, 1, 1, minus 1. Okay, so this is on your midterm exam. If I have a symmetric matrix, it's similar to a diagonal matrix with an orthogonal transformation. Okay, so let's do this. Come on, be nice to me. define a new random variable by y equals my orthogonal matrix times x. Okay. Let's assume that the mean of x is 0, just to make things simple. Okay. Then the covariance of y is the expected value of y times y transpose. Y is O times X, and this will be X transpose O transpose. Okay. These constants just come right out of the integral. So this is O, Q, O transpose. So that's 3, 0, 0, 1. Okay. Let's just do quickly. What is this y? It's 1 over square root of 2, 1, 1. Okay, so this is x1 plus x2, x1 minus x2. Okay. Okay, so what have we done? By knowing something about symmetric matrices, we do just a linear combination, a different linear combination of our random variables, a transformation of our random vector, and then this random variable has 3 times as much uncertainty as this random variable. So which one do you want to use to form your estimates on? Okay, so this gives you an understanding of the relative uncertainty and uncertainty in your measurements. So this combination is the one that's much more interesting. Okay, so when your covariance matrix is diagonal, it was trivial to understand the relative spread about things. When it's not diagonal, diagonalize it. It always exists with an orthogonal transformation. It's just giving you random variables that are linear combinations of your original random variables, and now you understand that the covariance of y is a diagonal matrix, and this one has much more information than this component. Okay, got it. One last thing, and then we're done with this. We define the covariance of a vector x. The variance is okay, so this is 1 by 1, n 1 by n. n by 1. So the variance of the random vector is the sum of the variances of the components of your random vector. So it's a trace of the covariance matrix, okay? And this will be an important norm for us. Okay, so this is a scalar. This will be the important norm squared for us. How about that? Okay. Okay, let's do a quick recap. I can tell you guys are tired. Me too. As engineers, unfortunately, random variables are not very interesting. It's random vectors that we need to work with. Each component is a random variable. If we have to do things with densities, we have a nightmare facing us because we have these iterated integrals. There's two very important quantities. One is the mean vector, average value of each of the components. That one makes sense. And the covariance matrix, which gives us much more information than just the variance, because it breaks out each component of the matrix is how xi about its mean is related to xj about its mean. If we have to compute that with integrals, we're going to be in big trouble. We need to understand right now their physical interpretation. It's still true when this matrix has very large eigenvalues. The eigenvectors in those directions are highly uncertain, and the eigenvectors corresponding to the small eigenvalues, those are where you have good information. That's what this factorization of Q as an orthogonal matrix times a diagonal matrix times the orthogonal matrix transpose does. It gives you directions of this matrix with the uncertainty, which corresponds to linear combinations of the original random vectors that have higher uncertainty all the way down to the lowest amount of uncertainty. Or you could say the highest information down to the lowest information when you look at the inverse. Q is diagonal, it's all very simple. When Q is not diagonal, this is where, remember, we built this from the eigenvectors and we just normalized them to have length 1 to get our orthogonal matrix. These are the eigenvalues. Big eigenvalues, high uncertainty, small eigenvalues, low uncertainty. Small eigenvalues, high information, the eigenvectors in those directions are the directions where you have high information in your measurement, for example. Eigenvectors corresponding to eigenvalues that are large, you have lots of uncertainty, low information. Okay, and this is just decomposing Y with a norm 1 transformation. It's orthogonal, and it diagonalizes it. That's just doing what we just said with eigenvectors in terms of directions. That's all it is. Okay, so we'll use this information when we're forming our estimators, and the weight that we use will come from the information matrix, the inverse of the covariance. Okay, so that's where this stuff comes from. The weighted least squares arises from the probability density, because this is the weight. And we will extract it in terms of the covariance matrix. That's a weighted least squares. It's a weighted least squares norm. Okay, thank you. That's it.